Welcome to the Deep Dive.
Great to be here.
Today, we're really getting into something foundational in computer science. How you build a heap data structure, starting from just, well, a plain list of elements.
Yeah, it's a core operation, and, understanding the efficient way to do it and why it's efficient, that's super important for anyone working with data structures.
Absolutely.
Yeah.
And our guide for this is section 8.2, Building a Heap, from the Hello Algo text. It lays things out really nicely.
It does, yeah, it's a clear explanation.
So our mission for this deep dive is to unpack the different methods for doing this heap construction. We want to understand the approaches and really nail down why the recommended one is the most efficient.
Exactly. We want you, the listener, to finish this knowing the how, the why, and the performance trade-offs.
Okay, so let's start simple. What's the basic idea? We have a list, could be numbers, could be anything with a comparable value.
Right, just an unordered collection. And the goal is to rearrange these items into a heap structure. That means, say for a max heap, every parent node has to be bigger than or equal to its kids.
Or less than or equal for a min-heap. You're imposing that specific order.
Precisely. And this whole process, taking the list and making it a heap, that's formally called the heap construction operation.
Okay. And the source, Hello Algo, it talks about two main ways to tackle this.
Yep, two key methods.
Let's dig into the first one. The source calls it implementing with heap insertion operation. This feels like the most straightforward way, maybe.
I think so. It's probably what many people would try first if they were figuring it out from scratch. You start with absolutely nothing, an empty heap.
Right, just your list waiting on the side.
Exactly. Then you just go through your list, element by element, pick one up.
And do what with it?
You perform a standard heap insertion, add that element into your heap that you're building.
Okay, and standard insertion. That means you stick it at the next available spot, usually the end of the array representing the heap.
That's right. You add it to the bottom rightmost position conceptually, but just putting it there probably breaks the heap property, right?
Yeah, it could be way smaller than its new parent or larger if it's a min-heap.
Exactly. So after adding it, you have to fix things. You perform what's called a sift up, or sometimes bubble up. You compare the new element with its parent.
And if they're in the wrong order, swap them.
Swap them. And you keep doing that, compare with the new parent. Swap, if needed, moving the element up the tree level by level.
Until it's in the right place, either because it's smaller than its parent for a max heap, or you've hit the root.
Precisely. So you repeat this for every single element in your original list. Add, then sift up, add, then sift up.
The source describes this as building the heap from top to bottom, which is maybe a bit counterintuitive since the element moves bottom up, but I guess you're filling the structure overall.
Yeah, I think the idea is you're adding elements as if filling the tree level by level, even though the adjustment happens upwards. You're conceptually building the main structure downwards.
Okay, that makes sense. Now the big question. How fast is this? Or what's the time complexity?
Right, so you have n elements in your list. You're doing separate insertions.
And how much work is one insertion, that sift up?
Well, in the worst case, an element added at the bottom might have to travel all the way to the root. The height of a heap with n elements is proportional to log n.
So each sift up takes, at worst, time.
Correct.
Okay, so if we do n operations and each one is O(n).
Which gives a total time complexity for this method.
Got it. It's logical, follows directly from the process, and often that's a pretty decent runtime.
It is. It's not bad at all.
Yeah.
The source then says, hey, wait a minute, there's actually a faster way specifically for building the whole heap from an existing list.
Ah, okay. This is where it gets interesting. Method 2. Implementing by happifying through traversal sounds a bit more complex.
It feels less intuitive at first, yeah.
Yeah.
But it's clever. Step 1 is super simple. Just take all the elements from your input list and dump them straight into the array that will represent your heap. In the exact order they appear in the list. No sifting, nothing.
Whoa, okay. So you just have, like, a structurally complete binary tree based on the array indices, but the values are totally unordered. The heap property is almost certainly violated everywhere.
Pretty much guaranteed, yes. Except maybe for the leaves, trivially. So now you have this array that looks like a tree but isn't a heap.
So step 2 must be the fixing part.
Exactly. Step 2 is where the magic happens. You traverse this array, but in a specific order. The source says reverse level order.
Reverse level order, meaning starting from the elements towards the end of the array and moving backwards towards the beginning.
That's right. And for each element you visit that isn't a leaf node, you perform a top-to-bottom heapify operation, which is also called sift down.
Okay, wait. Couple of things there. Why only non-leaf nodes?
Good question. Think about what a leaf node is. It has no children. The heap property compares parents and children.
So if there are no children, the property can't be violated. A single node is always a valid heap.
Exactly. So no work needed for the leaves. They are already, by definition, valid little subheaps. Saves about half the nodes right there.
Okay, that makes sense. And the reverse order traversal, bottom up through the tree levels. Why is that so important?
This is the absolute key insight for this method. When you process a node using sift down, you need its children subtrees to already satisfy the heap property for the sift down to work correctly.
Right, because sift down compares the node with its children and swaps it with the larger, or smaller for min-heap, child if needed, then continues down that path.
Precisely. By going in reverse level order, you start with the lowest level of non-leaf nodes. When you process any node at, say, level K, you are guaranteed that all nodes below it, at levels K+1, K+2, etc., have already been processed.
Meaning their subtrees have already been turned into valid heaps.
Yes. So when you call sift down on the current node, you know you're comparing it against children who are roots of valid subheaps. The sift down operation will correctly place the current node within that already structured part of the tree.
Okay, I get it now. The order ensures the necessary precondition for sift down is always met. You're fixing the heap property layer by layer, starting just above the leaves and working your way up to the root.
That's why the source calls this building the heap from bottom to top. The heapification work flows upwards from the bottom.
And where exactly do you start this reverse traversal?
You start at the index of the parent of the very last element in the array. That's the last non-leaf node. Then you just work backwards, index by index, down to index 0, the root.
Got it. Index floor down to 0, roughly.
Yep, that's the one.
Okay, this feels different. Method 1 builds it incrementally. Method 2 throws it all together, then fixes it from the bottom up. Now, the complexity. This has to be where the payoff is.
Right. Let's analyze method 2.
So my first thought, like the source mentions, is okay. There are about non-leaf nodes we process.
Roughly, yeah.
And a single sift down, just like sift up, can take time in the worst case, right? If an element at the root has to go all the way down to a leaf.
Correct. The maximum path length is the height of the tree. So
nodes times per node. That still looks like the same as the first method. Where's the improvement?
And this is exactly where that naive analysis goes wrong, as the source points out. It's not on log.
Why not? What are we missing?
We're missing how the work is distributed across the tree. That cost for sift down only applies to nodes high up in the tree, like the root or nodes near it. They have a long potential path downwards.
Okay.
But think about the structure of a binary tree. Where are most of the nodes?
At the bottom, near the leaves. The number of nodes doubles with each level going down.
Exactly. The vast majority of nodes are in the lower levels. And how much work does sift down take for a node that's, say, just one level above the leaves?
Well, it only has children that are leaves. So it compares with its children, maybe just one swap. That's constant time, like 01.
Precisely. A node 2 levels above the leaves might do at most 2 swaps. Still very little work. The amount of work for sift down is proportional to the height of the node itself, its distance to the furthest leaf below it, not the total height of the tree.
I see. So we have many nodes at the bottom doing very little O1 work, and only a few nodes at the top doing the maximum O log n work. The simple multiplication average doesn't capture that.
You've got it. The accurate analysis needs to sum the work level by level. You calculate number of nodes at level I. Max work for a node at level I.
And the max work for a node at level I is related to its height, which is like total height I.
Right, so you end up summing something like 2i time or time, where it's the total height and I is the level index starting from the root.
The source shows the math for this sum. It uses a technique, multiply by 2 and subtract.
The method of differences, yeah. It's a standard trick for summing series like this when you work through that algebra.
Which we won't do live on air.
Probably wise. But the result you get is that the total number of operations comes out to be roughly proportional to 2 plus 1, something like 2 plus 1 H2.
Okay, so the total work is roughly 022, but how does that relate to the number of nodes?
Well, for a reasonably complete binary tree of height, the number of nodes n is approximately 2 plus 1, 1.
Oh, so n is roughly 2 plus 1. That means 2i is directly proportional to n.
Exactly. So if the total work is proportional to n, the total time complexity is linear time.
Bingo! Linear time. Building the entire heap from scratch using this bottom-up sift-down approach takes only n time.
Wow. That's actually amazing. It goes from the intuitive to just by
Yeah.
changing the approach and analyzing it carefully.
It really is a beautiful result. It leverages the tree structure perfectly. Most nodes do almost no work, and the total sums up linearly.
Okay, let's recap quickly. Method 1, insert one by one, sift up. Intuitive, but oh. Method 2, dump all elements in, then starting from the lowest non-leaves, sift down each one, working backwards to the root. Less intuitive, but surprisingly efficient in Beck.
And the key is that the O log n cost of sift-down only affects a few nodes high up, while most nodes near the bottom take constant time, making the overall sum linear.
That's the core insight. The distribution of work matters.
So for you listening, knowing you can build a heap in linear time that's really powerful, where does this actually make a difference? Why should you care about this build?
Oh, it's crucial in practice. Think about heap sort. The very first step of heap sort is to take the unsorted input array and turn it into a max heap.
Using this build process.
Exactly. That makes the initial setup phase of heap sort super fast. If it were just to build the heap, heap sort wouldn't be as competitive.
Right. The sorting part afterwards involves extractions, each taking O log, so that dominates anyway, but having a fast start is good.
It is. And maybe even more importantly, think about priority queues. They're built on heaps. If you need to initialize a priority queue with a large batch of items.
Like setting up tasks in an operating system scheduler, or maybe nodes in Dijkstra's algorithm for shortest paths.
Perfect examples. You often start with a collection of things you need to prioritize. Being able to build the initial priority queue, heap instead of ON, can be a significant performance win, especially for large N. It gets the whole process started much faster.
So understanding this build isn't just academic, it directly impacts how fast certain fundamental algorithms and data structures can operate, especially during initialization.
Absolutely. It means that the cost of getting your data into the heap structure is minimal, essentially linear. You pay the logarithmic cost later for the individual operations like insert or extract min-max, but the bulk loading is cheap.
That really reframes how you might think about using heaps. If the setup is fast, you're more likely to use them.
It definitely makes them more attractive for problems where you have a large initial data set to organize.
Fascinating stuff. It really shows how a different perspective on the algorithm leads to a big efficiency gain. Thanks for walking through that analysis.
My pleasure. It's a classic example of smart algorithm design.
And for all of you listening, the final thought. You can take chaos and unsorted list and impose heap order on it in linear time. Where else could that initial fast structuring be critical? How does knowing about this n build change your approach to problems needing priority or order? Something to think about.
Definitely. Until next time on the deep dive.